All right, so let's do a couple of additional activities to wrap up our study of first-order partial derivatives for now, by thinking again in a little bit more depth and context about what first-order partial derivatives are telling us about a function of several variables. So the first activity that we'll do just presents us with a contextual problem where we have a function of several variables that comes out of oceanography, and we find the partial derivatives of that and then sort of discuss what those partial derivatives are actually telling us. So in a way that would be appropriate to a non-specialist audience, right? Maybe if you're writing for the journal Nature, you're probably writing in a different voice than if you're writing for Scientific American magazine compared to if you're writing for USA Today, right? I think for our purposes in this activity, we're probably going to want to aim for maybe the Scientific American level of description of what these partial derivatives mean. So assume your audience can sort of, read at an 8th grade level or better and has some working understanding of some scientific terms and things, but doesn't necessarily have to be the experts and doesn't necessarily have to be, USA Today, which I think is supposed to be readable at a 2nd or 3rd grade reading level or something like that. So we'll do that, and then we'll also talk about ways of estimating partial derivatives from other kinds of information about a function. So to get started, we talked about this a little bit at the outset today, about what partial derivatives actually tell us about functions of several variables. Because a partial derivative tells us the slope of a tangent line to a trace, a vertical slice in the coordinate directions of the graph of a function, that means that we can interpret first-order partial derivatives as a rate of change of a function, of a quantity, when only one of those variables is changing. And so this activity is going to ask you to do some interpretations of partial derivatives of this nasty-looking function, which is so messy-looking that I have to imagine it's actually an accurate scientific model, of the speed of sound in ocean water as a function of the temperature of the water, the salinity, so how much dissolved salt content is there in the water, and depth, how far below the surface are you. And so it's kind of a complex relationship because it depends on all three of these different things. And so it's going to have 3 different first-order partial derivatives. And so the question that you're being asked to think about and to write about in this question is, what do those partial derivatives actually tell us? And so there's sort of a 2-step process that I recommend, that I think this activity kind of tries to walk us through, to coming to an interpretation of what a partial derivative means. And for me, the first step is figuring out units. So when we're doing a contextual problem where our variables are actually modeling measured quantities in the real world from science or social science or whatever, then those quantities themselves, the variables that are being related together by this function, have units and they have physical meanings. And so the derivatives that we compute should also have units and physical meanings. And very often, once we've written down what the units of these partial derivatives are, that will suggest a good way to think about an interpretation of them. So let's just do, without calculation, because I want to leave the calculation part to you. Let's just sort of think about, if we were to take one of these partial derivatives, let's say the partial derivative with respect to t, right? Then what might that be able to tell us? So there are 3 different input variables that all affect the output here, right? The temperature of the water, the salinity of the water, how far below the surface are we? All 3 of those impact the speed of sound in the water. And so if I am coming up with a partial derivative with respect to t, what I'm really doing is I'm kind of measuring the rate of change along this one pathway here, by which the temperature determines the speed of sound, while we hold the other variables, the salinity and the depth below the surface, to be constants. And so that partial derivative, dc dt, well, remember where this comes from. So the definition of a partial derivative, right? If we were writing out the limit definition of this partial derivative, it would be the value of the function c at a point t plus h. So we're going to let that t value vary just a little bit from t to t plus h. But then we are not going to let the other variables vary at all. Right? So the salinity here is going to be held constant. So S is going to be the same in both of these function evaluations. The depth below the surface is going to be held constant. So D is going to be the same in both of these evaluations. And so what we end up with is something that looks like this. And then down in the denominator, we have an H. Right? Okay, but then the thing about each of these numerator and denominator, right, because C here means something. It means a speed of sound. And because H is an amount that I'm adding to my temperature variable, H has units of temperature. And the numerator has units of speed of sound. So if we do what's called the dimensional analysis on this, the units are the same as temperature, and the units up here are the same as speed, right? So what that's telling me is that this denominator is going to have the same units that T had, and those units are degrees Celsius. Oops. So I'm just going to kind of write that down here, degrees Celsius. And then my numerator is going to have the same units as my output variable, which is the speed of sound, and that output variable here is being measured in meters per second. So my numerator here is going to have units of meters per second. And so at the end of the day, if I were to compute out this derivative, it's going to have units that are derived units that we get by dividing the units of the numerator by the units of the denominator. So the units of my output of my function, which are meters per second, divided by the units of the input, which is being allowed to vary here, which is the units of my temperature, which is degrees Celsius. And so if you like, you can write this as meters per second per degree Celsius. Meters per second. And sometimes I'll put a little comma in here, per degree Celsius. And so that's how we would sort of describe the meaning, or at least the units of this partial derivative. And so now that we know that those are the units that we would be looking for, I think from there we can sort of write an interpretation of this, that it sort of tells me at what rate does the speed of sound in my water, at what rate does the speed of sound vary per unit change in the water temperature. So that's kind of the interpretation of what this partial derivative ought to be telling me. And I guess the one other thing I would do with this is just kind of say, when I say unit change here, very often when I write down a sentence that interprets a derivative, usually sometimes what I'll say is something like, for every 1 degree increase. For every 1 degree increase in the water temperature, right? And so if I do this calculation and it comes out with a number, let's say it's 0.2 or something, then that tells me that, actually, would it go that way? No, I think it'd be the other way, negative 0.2. And so if I get a number like negative 0.2, that tells me that at whatever point that I'm currently at, right, that if I were to increase my water temperature, then the speed of sound in that water is going to decrease at a rate of 0.2 meters per second for every degree of increase in the water temperature that I affect at that point. So it's sort of a two-step process. First, figure out what units that you should have for these partial derivatives. Then the next step in this particular activity is to actually do the calculation, do the computations of those partial derivatives, and then evaluate them at a certain point. So if we're at a place where the water temperature is 10 degrees Celsius, the salinity is 35 grams of salt per liter of water, and we are 100 meters below the surface, then the question is just sort of asking you, what does the sign, SIGN, of each of these partial derivatives tell us about the behavior of the function c? So what does it tell us about the speed of sound in ocean water, just by looking at what the signs of those three partial derivatives are? All right, so at the end of the day, in this problem, you computed these partial derivatives, interpreted them with their units. So we already talked about the interpretation of the t partial derivative. The s partial derivative would have units of meters per second per grams per liter, right? So it's this really messy derived SI unit, but the meaning of that would be, how does the speed of sound in water change as we add additional salinity to the water? So as
Excuse me, Professor, you are muted.
I am muted. Let me try that again. So you just heard me in the video, but not in person. Yeah, everything I just said was actually in the YouTube video now, but it's not in, you didn't just hear it. So let me say it again. So CS has those units of meters per second per gram per liter. And so it tells you how how the speed of sound in water changes as you vary the salinity. So as you increase the salinity by 1 for every gram per liter that we increase the salinity, it tells us the rate of change of the speed of sound. And then CD would have units of meters per second per meter. So if we wanted to be really clever, we could cancel out those meters and just call the units 1/second, which is weird, right? So usually I wouldn't do that if we're trying to actually come up with a good interpretation for this, which you did. It's the rate at which the speed of sound changes for every additional meter that we go further below the surface of the water. So you compute these partial derivatives. This team found out that all three of those partial derivatives were positive. And so if I want to increase the speed of sound in my water, I can either make my water warmer, or I can make it more saline, or I could make it further below the surface.
Application, excuse me, for D, alpha is 0.0.16.
This one here,
Alpha is 0.016.
I think that's what
Yes, okay.
that's what your team had there. Yep.
Okay.
So the one that I'm surprised about, and I might recommend just revisiting this calculation, is CT. Just thinking, again, if this is a legitimate physical model of the speed of sound, I think in water should be inversely correlated to the water temperature. So colder water should have a faster speed of sound. So I don't know, that might just be something to double check on there.